That is one strange-looking waveform. I think I've got some debugging to do. Hi, I'm Kevin. Welcome to my mess of a cave. I have too many projects on the bench at once. Last time, I showed some analog precision rectifier circuits. The best of the circuits, which prevented op-amp saturation, confused some viewers, because I apparently didn't make it clear that the full analysis involves going through several different phases of operation. Today, I'd like to clarify that and show some variations on a theme. I'll do another half-wave rectifier, and adapt the same basic circuit into a voltage clamp and a peak detector. All of these circuits start with the same basic idea. You start with a diode between your input and output ports. They differ only in what goes between the diode and ground. For the half-wave rectifier, we use a pull-down resistor to ground. When the input voltage is positive, the diode conducts and the output voltage mirrors the input. When the input voltage is negative, the diode is turned off, and the output will see only a resistor to ground. The half-wave rectifier is a special case of a voltage clamp. If instead of a resistor to ground, we have a resistor to some arbitrary voltage, which I'm showing here by deriving it with a potentiometer, we can clip the negative excursions of the output to that arbitrary voltage. When the input is above that voltage, the diode conducts, and the output follows the input. When the input is below that voltage, the diode turns off, and the output sees the clamping voltage. The peak detector works a similar way. Instead of using a resistor to a known voltage, you use a capacitor. The capacitor voltage marks the high point that the input voltage has reached. If the input voltage goes above this mark, the diode conducts heavily, and the capacitor rapidly charges to the new voltage. When the voltage drops below its peak level, the diode is cut off, but the capacitor is still charged to the peak voltage, and that's what the output sees. Of course, we usually want a peak detector to be able to detect more than a single peak, so we need some way to reset it. One thing you see a lot in peak reading meters and automatic gain controls is simply to put a big resistor across the capacitor. When the input voltage is below the peak, the resistor gradually drains the charge from the capacitor, preparing it for the next peak reading. All of these circuits suffer from the same problems. First, the diode will drop about 0.6 of a volt. We saw that last time with the half-wave rectifier, where the rectified signal only captured part of the positive input. What's worse, the input and output impedances were both too low. With not too unrealistic source and load impedances, we lost a big fraction of the remaining signal. We needed to fix that somehow. We recognized this as a case of needing to hide the monster. And we knew what to do. Enclose the problem circuit inside the feedback loop of an op-amp. This is only a little bit different from what we did before. I've added a resistor in the feedback path because I'm going to want one there shortly. This shouldn't affect the circuit performance much. The resistor is going to the input of an op-amp, so it shouldn't carry any current or drop any voltage. Let's get this on the breadboard using the half-wave rectifier circuit and see what happens. Before we continue, let me make a brief interruption. Many of you know that my content is never paywalled and is free for anyone to learn from. I never beg for money to support the channel. But I do ask something important, that you take care of one another. To that end, the advertising revenue from this YouTube channel goes to charity. My March 2025 payment has gone to the Get Fed Up campaign of Save the Children. The campaign has a single mission, fighting childhood hunger. Of course, that fight has more benefits, because the prosperity of a community depends on education, and you can't fill a child's brain when a child has an empty belly. But more important, I want children to be able to play and dream about their future without worrying where their next meal will come from. I know that Kevin's Cave people are a kind and generous lot, so I'm urging you to join me in supporting this organization, using the affiliate link up here, or down there, or at any rate somewhere nearby. I've set a relatively modest goal of $500. If even 1% of my subscribers were to give $10 apiece, we'd meet that goal and feed a classroom of 30 hungry kids for a week. I hope that instead we'll just crush it. Won't you help out today? I'm using an LMC6482 dual op amp in place of my usual TL072. I'll explain why I made that choice later in the episode. But that means I need to run at a lower voltage. I'll choose plus and minus 5 volts. I'll hook up power and ground, add some bypass capacitors, and a strap to make their leads as short as the breadboard will allow. I'll stick in the forward diode. I'm using a Schottky BAT41 so as to get the smallest voltage drop I can. I'll wire that between the two halves of the op amp. In goes the 20K feedback resistor and the pull down to ground. The output of the buffer gets jumpered to the negative input and pulled down to the ground. I'll add leads to the AWG and a scope probe monitoring the input and finish up the feedback connection. Oops, I got the alignment wrong up top. That chip carrier is taller than it looks on camera, and I need to look around the camera to see the board. No harm done, I'll fix it. And just then, the breadboard camera's battery ran out. But I hooked up the second scope probe, turned on the circuit, and saw a weird output trace appear. I zoom in on the scope, and it's oscillating at about 400 kilohertz. We've seen this sort of thing a couple of times now. Each op amp delays the signal a little bit. So a signal at the circuit input will appear a little bit later at the diode, and a little bit later still at the circuit output. If the delay is half a cycle at some frequency less than the frequency where the overall circuit gain falls to unity, our negative feedback changes to positive feedback at that frequency. The circuit will oscillate. The solution is simple. Slow down one of the op amps to roll off the gain at high frequencies so that the loop gain falls to less than 1 before the phase shift reaches 180 degrees. We can do that with a capacitor in the feedback loop. Let's poke around and see what its value should be. There are fancy ways to calculate it, but they're all enough work that most of us resort to trying different values to get the right one. 100 picofarads is usually a good starting point for this type of circuit. We'll start with that. And sure enough, the signal cleans right up. But to make sure that we've got the right value, we should switch to a square wave, since the sudden transient is what's most likely to start an oscillation. The square wave input is overshooting a little. That's not that uncommon. The function generator is overcompensating for the load capacitance. Let me zoom in on just one transition. The rise of the output signal is a little slow and sloppy. If the circuit can stay stable with a smaller capacitor, that's what I'll want to use, to make it as fast as possible. How about 33 picofarads? That's too small. The output is overshooting, indicating that we're just on the verge of oscillation. Split the difference, 68 picofarads? That looks pretty good. It's not overshooting, it's just rising smoothly. I'll say 68 picofarads is the Goldilocks value. Now let me zoom back out and look at how the circuit behaves at a higher frequency, say 20 kilohertz. The delayed response of the positive going transitions is clearly not acceptable. We saw that last time too. It's the result of the fact that when the diode turns off, the first op-amp output is driven to the negative rail. When the diode starts conducting again, the op-amp output can move at only a finite rate, and it seems to be taking about 10 microseconds to move from the negative rail to catch up with the input signal. From some of the comments I've seen, it appears that I wasn't clear enough last time in explaining the glitch we're seeing at the positive going transition, so let me have another go at it. We'll start with the input voltage above ground. The diode will be conducting, and so the negative feedback loop can function. The op-amp on the input side will be doing what it must to keep its inputs equal, so the voltage at its inverting input must equal the input voltage. There's no current through the 20K resistor, because the op-amp's inputs draw no current, so the voltage at its other end must be the input voltage at well. If the diode is conducting, then the voltage at its anode must be a diode drop higher. As long as the input voltage stays positive, this whole circuit is a more complex version of a unity gain follower. As soon as the voltage goes below ground, the diode stops conducting. The output voltage of the circuit stays at ground. There's still feedback around the output buffer. The left-hand op-amp's inverting input is being held at ground, while its non-inverting input is below ground, so its output voltage falls rapidly. Still, it falls at a finite rate, so there's a brief period in which it's moving. Eventually, though, it reaches the negative supply rail. The feedback loop is broken, and the op-amp is saturated. When the input voltage goes above the ground again, the glitch begins. The voltage at the non-inverting input is now above the inverting input, so the output of the op-amp will now start swinging positive. But it started all the way down at the negative rail, so it will take a certain amount of time to come up. The diode is still turned off, so the output buffer stays at ground. Eventually, the output voltage of the op-amp will be at least a diode drop above the ground, and the diode will start conducting again. Now the output voltage can start to rise, also limited by how fast the op-amps can swing. During this period, there's still no feedback in play, but neither op-amp is saturated. They're both moving rapidly toward the stable state. Finally, the left-hand op-amp's output gets to a diode drop above the circuit input. The circuit output is a diode drop below that, mirroring the circuit input. The voltages at the left-hand op-amp balance, and the feedback loop is operating normally again. We can see all this behavior on the oscilloscope. The yellow traces the input, the aqua traces the circuit output, and the purple traces the output of the left-hand op-amp. We'll start with the circuit in the state where there's negative feedback. As long as the input stays above ground, the intermediate voltage is a diode drop above the input, and the output tracks the input closely. When the input drops below the ground, the output voltage is held at ground, while the intermediate voltage starts moving negative rapidly until it hits the negative rail. It can go no lower, so the output will stay fixed at ground as the cycle continues. When the input goes above ground again, the left-hand op-amp needs a brief delay to recover from saturation, and then its output voltage climbs rapidly. But nothing happens to the circuit output until the op-amp is a diode drop above ground. Then the outputs of both op-amps climb at the op-amp's slew rate until the output is once again tracking the input. Now that we understand what's causing the glitch, what can we do about it? Well, in this circuit topology, we can clear up most of the problem just by adding one more diode to provide negative feedback in the left-hand op-amp during the negative part of the cycle. When the first diode is conducting, the circuit output is tracking the input just as before, so the left-hand op-amp must be providing a voltage a diode drop above that. The new diode is reverse biased and turns off. The new circuit will perform just like the previous one on most of the positive half cycle. When the input dips below the ground, the original diode turns off, and the circuit output clamps to ground as before. For the moment, that ground appears at the input of the left-hand op-amp. The output of the first op-amp starts swinging rapidly in the negative direction. But it can't go very far. Once it's a diode drop below ground, our new diode turns on, and we have a feedback loop around the left-hand op-amp. Its inverting input is above its non-inverting input, so its output continues swinging rapidly downward until it reaches a diode drop below the input voltage. At that point, the two op-amp inputs are at equal voltage. The output of the left-hand op-amp will track a diode drop below the input voltage. Now we see the purpose of the resistor in the feedback path. Its left hand is going through a diode to an op-amp output pulling down to a negative voltage, and its right hand is going to an op-amp output pulling up to ground. If it weren't there would be a large current through the diode and unpredictable voltages at the two op-amp outputs. Some op-amps don't have internal current limiting, and this configuration would even burn them out. The resistor keeps the current on the negative half cycle to a manageable value and keeps the voltages on the two op-amps independent of one another. Now let's have the input voltage rise above ground again. The top diode stops conducting because the voltage across it is now less than a diode drop. The inverting input to the left-hand op-amp is tied to ground again through the 20K feedback resistor. The voltage of the op-amp output rises rapidly, but once again it doesn't have far to go. Once it gets to a diode drop above ground, the lower diode starts conducting, and the circuit's output rises too. Once it's equal to the input voltage, we're back to the case we started at. This will give us a much shorter glitch. The op-amp doesn't need to recover from saturation, and its output needs to move only 2 diode drops, rather than coming all the way from the negative rail. We can see how well it works by plugging in the second diode. It's worth noting that for this test I'm using BAT41 Schottky diodes for their low forward voltage drop. That will make the glitches even smaller. The scope traces are much cleaner after the second diode goes in. I can take it up to a frequency well beyond the audio range. At 50 kHz, the output wave is still decently clean. I'm pretty happy with this circuit. To make the glitches take an even shorter time, we will simply have to find a faster op-amp. The key datasheet parameter to look for is slew rate. This table gives you an idea what you can expect for inexpensive and best-in-class op-amps of the 3 major types: bipolar, JFET input, and CMOS. The relatively inexpensive CMOS op-amp I'm using here is hardly the best available. Of course, I chose it for other reasons. One was cost. There can be a couple of orders of magnitude difference in price between the cheap common types and the premium best-in-class ones. Another is the fact that the LMC6824 is an op-amp type that I keep on hand. But the key factor was that I wanted to use the LMC6824 in the peak detector, where there was another parameter that took precedence over the slew rate. But I'm going to keep you in suspense about that one for a while longer, while we look at the voltage clamp. And now we've done almost all the hard work for hiding the other 2 monsters in the feedback loop. To turn this circuit into a voltage clamp, all I need to do is unground the pull-down resistor and connect it instead to a variable voltage source. A potentiometer will do fine. This circuit will clamp the negative peaks of a signal. If I wanted to clamp the positive peaks instead, all I'd need to do is reverse the diodes. But let's start with the clamp on the negative peaks, the way they were in the half-wave rectifier. Here's the circuit with the changes made. I've pulled out the 10K resistor to ground, and instead I wired in a 10K resistor to a potentiometer whose ends are connected to the supply rails. Just for a change, I'm giving the circuit a triangle wave. With the pots centered, it works just like the rectifier we had before, but now I can move the voltage threshold up and down to decide where to clip the signal. And I love it when a circuit modification works on the first try. Now I'll try reversing the diodes. And sure enough, the signal now is clamped at the positive end. That was easy. And now we come to the final variant for today, the peak detector. To create it, we simply remove the pull-down resistor that we used for the rectifier or voltage clamp and replace it with a capacitor that holds the highest voltage that the signal has reached. Ideally, when the signal goes above the highest previous voltage, the forward diode will conduct and charge the capacitor up to the new voltage. Just as with the other two circuits, when the input signal falls to a low level, the feedback diode will conduct and keep the op-amp from saturating. Of course, as I said earlier, the peak detector needs another signal to indicate what time interval is being measured and reset the capacitor's charge. I'll do that with a MOSFET switch. If I put a logic high signal on the MOSFET gate, the MOSFET will conduct and dump the capacitor's charge to ground. I do have to worry that the current there won't be excessive. Fortunately for me, the datasheet for the LMC6482 that I'm using says that it's all right to short the output to either power rail, and that the current will be limited to 20 milliamps. I can live with that. The MOSFET I'm using to reset the circuit is pretty robust, and can handle with ease both the continuous current and the brief pulse of current when the capacitor discharges. I hacked up a quick circuit to subject the peak detector to a torture test. The design of that circuit would kind of break up the flow here, so I'm going to do a short bonus video describing it. Once it's up, I'll drop a link in the video description. The input signal to the peak detector, on the yellow trace, will be a series of trains of very short pulses, with each pulse being at a higher voltage than the one before it. The reset signal, on the blue trace, will be high for 2 pulse trains and low for the next 2. The output that I would expect to see is a stair-step for the first pulse train after the circuit is reset, then a continuous high voltage until the reset signal arrives, and then something close to ground until the reset signal falls again. I have the peak detection circuit on the breadboard here, with my test rig on a second breadboard below, providing the pulse trains on the blue DuPont wire and the reset signal on the orange one. I'll give it a nice medium-speed pulse train, and the output looks pretty good. A stair-step up, a more or less level period, and a pull down to ground when the circuit is reset. I can crank up the frequency some, and the circuit is still behaving well even when the pulses are only 4 microseconds wide. The feedback diode is absolutely essential to getting that performance. If I pull it out and retest, things look pretty good at low frequencies. But as I crank up the frequency, more and more of the stair-steps get lost, because the circuit can't swing out of saturation fast enough to track them. Before long, we're losing half the stair-steps, Putting the feedback diode back in clears up the problem, of course. I can run it where each pulse train lasts just over a millisecond, and the individual pulses are only 4 microseconds wide, and it keeps up just fine. Pull out the feedback diode at that speed, and the stair-steps disappear altogether. But we still have a problem at the low-frequency end. If each pulse train lasts about 15 milliseconds, then you can see the voltage starting to droop during the hold period. Slow it down to 150 milliseconds, and the droop is clearly damaging the output. And if I go all the way to 4 seconds for the hold period, the output is simply unrecognizable. Some peak detections obviously need a longer time than that. We need to do some detective work to figure out where the charge on the capacitor that holds the peak is going. But I'm about out of time for this video, so I'm going to have to defer digging into the fix until next time. I hope you'll stay tuned for that. If you don't want to miss it, maybe you should suggest to the YouTube algorithm that this is the type of content that you want to see. To summarize, in this episode, we looked at 3 examples of a diode in the feedback loop, and showed how we had to tame them all by avoiding op-amp saturation by introducing a second feedback diode. We learned that the slew rate, the rate at which the op-amp can change its output voltage, is a key datasheet parameter that we need to look for in these circuits. At the end, we saw a problem where the peak detector circuit can't hold its peak for very long at all. Next time, we'll fix that. Until then, stay safe, stay healthy, stay curious, and please take care of one another. And on the subject of taking care of one another, I'd like particularly to thank Danielle van der Bent, Andy Kirkham, Charles Lowmiller, Ray Otwell, John Shepard, and a half-dozen donors who wish to remain anonymous for their contributions to the Get Fed Up campaign at Save the Children. Kevin's Cave people are a wonderful lot. Thank you all. Bye.